Okay, so let's start our webcast, right? We still have, including today's, I plan to have three more lectures. So that means 2 lectures this week and 1 more next week, Monday. So try to finish chapter 7, which is the last chapter, within this week. If not, then we have to extend to next Monday. And next Monday, we may have to do revisions as well as to discuss about the midterm test. All right. Okay, so chapter 7 is on hypothesis testing. It is one of the very commonly used statistical inference methods. So, but we restrict our discussions mainly on problems that concerning about the parameters from normal distributions, normal populations. All right. So, okay. So what we're going to talk about is the testing based on normal distributions. So we'll mention or discuss about type 1 and type 2 errors. All right. In fact, we have to set the hypothesis, how to set hypothesis. And we also talk about level of significance, which is alpha, usually. And usually it takes 5% or 1%. All right. So then we talk about specific problems about hypothesis testings concerning about the population mean. So for hypothesis testings, the most commonly used approach is the p-value approach. That means we set up the hypothesis problems, do the calculations, and then at the end we come up with what we call p-value, and then we make the decision based on the p-value. But before the computer are available abundance, we use this called critical value approach. So you also have to be aware of the relationship between these 2 approaches and how to use any one of these 2 to make the decisions. Then we move on to talk about the difference test hypothesis concerning about the difference between 2 population means, as well as we talk about concerning about variance, and also okay, miss one more. We also talk about the ratio of the 2, or concerning hypothesis concerning about the 2 variances. All right. So now an alternative hypothesis. All right. So what is the hypothesis? Hypothesis basically is a statement and not a question. Hypothesis is a statement, which means that it has its truth value. That means it can be true, can be false. All right. So, for example, okay, we say that. All right. So I am 20 years old. So that is a statement. All right. The statement can be true, can be false. So obviously, I'm not 20 years old, so it's a false statement. All right. But for the statement or questions like this, what is my age? So this one it's a question, it does not have a true or false value. Or we don't know whether it's true or false. So in that case, that is not a statement or not a hypothesis. So a hypothesis, all right, is a statement which has a truth value. That means it can be true or it can be false. All right. A statistical hypothesis is some statement concerning about the properties of the populations. So to make it easy for us, so what we discussed is only about mean and variance, these two parameters of the populations. In fact, we also limit our discussions to normal populations. All right, so we will use the term accept, although I say reject. All right. In fact, when we say accept, it simply means we do not reject. All right. So we use these two terms. Now, when we say we reject certain statement, for example, a simple example is that, okay, a statement mu equal to 3, for example. So this can be right, or can be true, can be false. All right? So what we do is to base on, if you know the population, you check everyone, and then you can calculate. So if the population mean turn out, after we calculate, look into everyone, mu equal to 2.999. Then this statement is still false because that's not equal to 3. But in general, we don't have the answer. We are not able to evaluate everyone and then get the answer. So this is just it's not very practical to get the value mu. So usually what we do is to take a subset of the population, or we do a sample, and then we calculate X bar. So for example, X bar equal to 2.99. All right. So now we have to make a decision whether we believe that mu equal to 3, or we don't believe that mu equal to 3. Or in other words, whether we should reject the hypothesis or do not reject the hypothesis that mu equal to 3. All right. So if X bar equal to 2.99, will you believe that mu equal to 3? Yes? No? I don't know. Is 2.99 very close to 3? Is it close to 3? Yes, it obviously, right? But if I tell you that this X bar come from a population, all right? Okay. So suppose the population, suppose mu equal to something, and the standard deviation, not the standard error, not the variance, the standard deviation is like that. All right? And now I take a sample, let's say a sample of 100, and then I calculate X bar, and the X bar turned out to be 2.99. So I asked, if mu equal to 3, how likely you see X bar equal to 2.99? Can we answer that question? Is it likely or unlikely? So we have to, that's why we learn all the probability, right? So I asked, okay, what is the chance that X bar greater or equal to what I observed, 2.99, given that mu equal to 3? All right? Or maybe probability of X bar less than 2.99 given mu equal to 3. All right? We look at both sides. We don't know, so we calculate this probability. All right? So if mu equal to 3, is it likely to have X bar equal to 2.99? Where the population with a standard deviation is very, very small. In fact, what does this sigma equal to 0.0001 mean? It means that it's very likely the X, the value of X is around, all right, 2.9997 and 3.003. This is the range. It's most likely you will find majority of the data, majority of the observations fall within this range. So you take 100 of them. So the average should be very close to 3. And now you see 2.99, which is off the mark. In fact, this probability, you have to standardize it. And remember, the variance of x bar is equal to 0.0001 divided by square root 100. It's even smaller, all right, the variance of x bar. All right, so if mu is really equal to 3, you expect x bar should also have a mean equal to 3. And it's deviate from this center only by 0.000, another 0, 1. All right, why is another 0? Because it's divided by square root 100. So my point is, you cannot just look at the value of x bar. You have, this is important, you have to take into consideration the variation of the data, or the standard error of x bar, how x bar vary. In fact, x bar vary very small range. Okay, so if it is mu really equal to 3, you shouldn't see 2.99 for the x bar. All right? Okay, so anyway, the idea is that take a sample, calculate something, and then if you believe what you observed is likely, if mu equal to that value, then we do not reject the statement. But if we find that it is unlikely to have such thing, if the statement is true, then we will reject the hypothesis. All right? So now the problem here is how to set up the hypothesis. So usually, the hypothesis that we set as what we call null hypothesis is the hypothesis that we believe, or it is status quo. So usually the alternative, the other one, alternative choice, is the one that you want to establish. So for example, if I have a new medicine, I want to claim that this is better than the existing one. So I have to set, maybe I measure as the probability or the proportion of patients that cure from certain disease. I have to set that higher than the existing belief. So I set that as my alternative hypothesis, and my old one is that, okay, my new medicine is as good as the existing one. So it's the status quo. And I want to find evidence to say that the new drug or new medicine, in fact, is better than the existing one. All right? So just remember, when you try to set the hypothesis, usually it's the status quo or nothing changed is the null hypothesis. While the alternative means that there's something changed, something different about the existing belief. All right? So we'll discuss this again, but that is how we set up the hypothesis. All right? So we formulate the hypothesis that we want to reject. All right? So usually, but not always, and in this module, we try to set the hypothesis at an exact value. That is, your null hypothesis denoted by H0 usually is something like this. All right, equal to certain value, like 3, for example, or in general, write it as mu naught. So this is a fixed constant. So it's equal. So the alternative can be mu greater than 3, or another one is mu less than 3, or mu does not equal to 3. So there are these different types of the alternative hypothesis. All right, so the rejection of H0 leads to the possible acceptance of the alternative hypothesis. All right, so it may consist of several values or infinite number of values. For example, even this one have infinite number of values. Any value greater than 3 is considered as the alternate values. All right, let's look at this example. Now, we wish to determine whether the mean IQ of pupils of a certain school is different from 100. All right, different from 100. It did not specify whether it is higher than 100 or lower than 100. So it's only different from 100. So that's what we want to establish. So our null hypothesis, all right, in this case, is mu equal to 100. All right, so this means that, okay, it's just like average, mu equal to 100, and we want to find out whether this particular population, all right, this particular school, the students from this particular school, or in this particular school, okay, has an IQ which is different from 100. All right, and so the alternative is mu does not equal to 100. Now this is called a two-side alternative. This one is a two-side alternative. All right, two-side alternative. And for a two-side alternative, we apply a procedure, a test procedure. It's called a two-side test or two-tailed test. All right. So this is called two-side alternatives, and then the test used to test the two-side alternative is called a two-side test. So it's a little misleading here, but the test used, later on we will talk about what a test is, all right? But a test used for testing the two-side alternative, this is a two-side alternative. Why is it two-side? Because mu does not equal to 100 is equivalent to mu greater than 100 or mu less than 100. So it's two-side, all right? So another scenario is that, okay, suppose we're interested in finding whether the mean IQ of the pupils is greater than 100. Then in that case, the alternative is a one-side alternative. So in other words, we are looking at mu greater than 100. Greater than mu, the alternative mu greater than 100. All right. But if you believe or you want to find out whether the mu is really less than 100, then your alternative is mu less than 100. So our null hypothesis is still mu equal to 100. All right. That is what everyone should be, that we believe. Now I want to find evidence that this is the mu, in fact, is not 100, but maybe greater than 100. Then our alternative is like that. Okay, sometimes it's important that you have to set up the right alternative. So for example, it turns out that maybe the average ability of the student, all right, the average IQ for a sample from this school with X bar, all right, X bar equal to, let's say, very high, let's say 125, all right, then this one will not lead, okay, also assume sigma, let's say, equal to 3, all right, very small, and n equal to 25, for example. Then this one is very unlikely come from a population with mu equal to 100. It most likely mu is bigger than 100. But if you choose, when you start with alternative mu less than 100, so even this, what you see is very extreme against mu equal to 100. But because your alternative set as mu less than 100, in that case, we do not reject the null hypothesis. That means that evidence is not favor to the alternative. So that's why setting the alternative is very important, because it decides on how you do the test. All right. So it's important that you have to set the right null hypothesis and the right alternative. All right. So in this case, if you want to test mu equal 100 against mu less than 100, so even if you find out the X bar from the data, it's likely that you believe that mu is bigger than 100, but then you cannot reject the null hypothesis mu less than 100. Then you may think, okay, in that case, since I see X bar equal to 125, can I test this hypothesis now? So for normal people, yes, this is the way. Okay, I check. Okay, X bar is so big, so I may check the alternative, test mu bigger than 100. But in fact, you cannot change. You have to set your hypothesis before you look at the data. Once you look at the data, then you swap or you change your hypothesis. There is some kind like a cheating. So we don't do that. We have to set the hypothesis before you do any statistical analysis, do any computation. So you have to set the hypothesis. And how do I know which one to set? Then it's based on the problem that you are asked to deal with. All right. If you believe that mu is less than 100 for this particular population, then you set it as it is. So if in case you don't know anything about whether it's bigger than 100 or less than 100, then to play it safe, set as not equal. That means we consider both, so long as it's different from 100. So we've set two-side alternative. So in other words, if you have no information about which direction, whether it's greater than mu naught or less than mu naught, then you put it as not equal as your alternative. All right. So in that case, you don't have to specify which direction to go, so long as it's different from 100. Okay. So here's the idea. Oh, shit. Okay. So we have a claim. The population mean of age is 50. So that is our hypothesis, mu equal to 50. All right. So we have this population, and we take the sample. We take a sample, a random sample. And then from the sample, we calculate x bar equal to 20. Then we ask ourselves, is x bar equal to 20 likely if mu equal to 50? All right. If the population mean is 50, is it likely to see x bar equal to 20, the sample mean of a random sample from this population? Now, if it's not likely, then we reject this hypothesis. All right. So that's the idea behind. So basically, here the alternative is mu does not equal to 50. All right. So mu does not equal to 50. Now I take a sample and find the sample age. So it's just like, okay, if I make a statement, okay, the average age of the NUS students is 50. So this is my statement. All right. So what I believe. So I set the alternative of mu does not equal to 0. Okay, 20 is not NUS students. Okay, let me change it to 25 maybe. All right. Then I take a sample of NUS students and find the sample mean age is 25. Then is it sufficient to say that the mu equal 50 is the wrong statement? All right. So obviously it's unlikely that if the mean equal to 50, then the x bar equal to 25. Oh, here I also want to emphasize. Just now my example is NUS population, student population. All right. So use of common sense. General university student majority are maybe teenagers or just early 20s. So the average age cannot be 50. Okay. So this is correct, but not from statistical point of view. Statistical point of view, there are only two things. Either you ask everyone in NUS students, every NUS students, get their age and then take the average. That is a true answer. All right. There's 30 or 40 something thousand students. All right. Another one is to take a random sample of, let's say, 30 or 100, for example. Then look at that sample mean, and then do what we're going to do the hypothesizing and then make the decision. All right. So my point is, we have to use statistical method to support our argument, not use common sense. Maybe someone don't believe, maybe suddenly NUS student population enhanced by including a lot of those alumni as well as those because we now promote lifelong learning, right? So we can students 70, 80 years old to take NUS course, considered NUS student. Then in that case, we may have a very big or old average age. So my point is that we trust our data. We don't use our other knowledge to try to draw a conclusion. We try to draw a conclusion from data. Okay, so, all right. So this is what we do. So this is the distribution of x bar. Distribute x bar. Suppose if x naught is true, the mu is equal to 50. So how likely we see x bar equal to 20? So we look at how unlikely, or what's the chance that you see something more extreme than 20. In this case, it's less than 20. All right. So that is the idea. if it's unlikely to see what you have in the sample, then you reject. Then you don't believe that the null hypothesis is true. All right? So that's the idea behind the hypothesis testing. So of course, hypothesis testing basically is a decision. So if I see this one, I decide whether I reject or do not reject certain statement. So that is the decision that we make. Whatever decision you make, there may be mistakes. All right? So here is the situation. So the decision that we make is to reject the null hypothesis or do not reject the null hypothesis. That is the decision that we are going to make based on the data and the procedure, that test procedure that we have. The other one is the state of nature. Okay, that means the true answer, which we don't know. So there are only two possibilities. One is that the null hypothesis is correct. The other one is the null hypothesis is not correct. All right, these two. And these two are the true answer, which we don't know. We only try to guess or try to make our decision whether I believe that H0 is true or H0 is false. So if H0 is true, all right, and I make a decision to reject H0, I commit an error. All right, so there's an error. But if H0 is false, I reject an H0, then I make the right decision. So I make the correct decision. All right, so no mistakes. On the other hand, if the null hypothesis is true, I do not reject it, again I make the correct decision. So no error. So only when the null hypothesis is false and I do not reject the null hypothesis, then I commit an error. So there are two scenarios that I have commit an error. One is when H0 is true, you reject it. So we reject wrongly. The other one is when H0 is false, but you do not reject it. So you still believe that it's true, so you commit an error. So to distinguish these two types of error, we give a very simple name, type 1 and type 2 error. All right. So type 1 error is the one that when null hypothesis is true and you reject it. Type 2 error is when the null hypothesis is false, you do not reject it. So, so in order to study the error, we'll try to, hopefully we want to have the chance of making an error as small as possible. So that's why we try to control these two types of error by minimize the probability. So we look at how likely we reject the null hypothesis given the null hypothesis is true. So we set that as alpha. So what we are going to do is to try to derive something such that the chance of rejecting the null hypothesis when the null hypothesis is true, all right, is only alpha. All right. While the other one, the probability of do not reject H0 given H0 is false, set as beta. All right. So alpha is the first Greek letter, beta is the second Greek letter. So represent the probability of type 1 error and probability of type 2 error. All right. Can I have 0 here? Alpha equals 0. Where H0 is true, the chance of rejecting H0 is 0. Can I do that? Is it possible? I draw a sample, look at the X bar. For example, I want to test mu equal to 50. I look at my sample mean. All right. So can I make it the probability or make it alpha equals 0? That means the chance of rejecting wrongly the null hypothesis is 0. Is it possible? Yes, it's possible. Very simple. Okay, look at your X bar. I don't care what X bar is. I always make the decision. I do not reject the null hypothesis. Okay, no matter what I see, I do not reject. Right? So I won't make this kind of mistakes. Wow, that's good. But what's the problem? Why we don't do that? Because what happens if the null hypothesis is false? Then I will commit the type 2 error with probability 1. So that's not good. So we try to balance between these two. All right? So that's why we need to learn statistics. So we try to balance between these two types, the chance of committing these two types of error. And usually we try to fix, because we cannot minimize both alpha and beta simultaneously. So we try to fix one of them. So we fix the alpha. So the alpha that we fix is either 5% or 1%. But in some situations, you may set it as 10%. The chance is, the idea is that, okay, I just want to take 5% risk that I reject wrongly the null hypothesis. All right? If I don't want to take any chance, then I just do not reject the null hypothesis all the time. Then I won't make a type 1 error. And the chance of making a type 1 error will be 0. All right? But that's not what we want, because in that case, you will increase your chance of committing a type 2 error. All right? So type 1 error, reject H0 when H0 is true, and it considered as a series type of error. All right? So why I say it's series, you can draw parallel with the court of law cases. So usually when the accused stand in front of the court, so the prosecutors will try to look for all kinds of evidence, arguments to prove that the accused is guilty. All right? So, but you don't want to make a mistake that when the accused is innocent and then you prove that he is guilty. So you don't want to commit that type of error. So usually in the court of law, the probability of committing a type 1 error, that means reject wrongly to say that an accused is guilty, but in fact it is innocent. You don't want to commit that error with a very high chance. So usually we try to put it 0, but it does not guarantee. So that's why in the court of law, it's very stringent. So, but in statistics, we set not as stringent as the court of law, we set at 5%. That means we allow to commit the error. When the null hypothesis is true, we may make the wrong decision, reject it wrongly, but only subject to 5%. So our procedure, what we do is try to limit the committing type 1 error with 5% because we think that is a serious mistakes. All right. Type 2 error is when null hypothesis is false and we're not rejecting the null hypothesis. All right. So this level of significance is the probability of committing a type 1 error. All right. So just remember the definition. Type 1 error is rejecting H0 when H0 is true. So the chance of rejecting committing type 1 error is called level of significance. It is alpha, and usually set at 5% and 1%. And this has to set in advance. That means before you look at the data, you have to set it. Okay, I decide to use 5%. Then you stick to it. All right. The chance of committing a type 2 error, we call it beta. That is, you do not reject H0 when H0 is false. That means H1 is true. All right, and that's beta. So 1 minus beta is called a power of a test, of the test that lead to your decision. So that is reject H0 when H0 is false. So that's good. All right, this is good thing. So this good thing, or the probability, as we want this probability of rejecting H0 when H0 is false as high as possible. So that term, we call it power of a test. That means how good your procedure is measured by this power of a test. Okay, so let's look at this scenario. So here, very simple. I have two statements. Mu equal to mu naught. That's what I believe. But I want to test against it and say that mu, in fact, is not mu naught, but equal to mu1. So here, this is when null hypothesis is true. The test statistics, Z here is supposed X bar minus mu naught over sigma over root n. So we'll discuss this in a while. But this is the test statistics. So based on the test statistics, all right, we decide that, okay, we do not reject the null hypothesis, all right, when the Z, let's calculate this one, falls here, we will not reject the null hypothesis. But when it falls in this range, we'll reject the null hypothesis. That is our decision. So the chance of committing a type 1 error, that means reject wrongly when the null hypothesis is true, the chance is, in fact I have it. All right, so this is alpha. This part is alpha, this area. All right, so that's how we decide to have a range such that below it, when z is below that value, this value, we do not reject the null hypothesis. But when it is bigger than that value, we reject the null hypothesis. And the chance of committing a type 1 error represented by this probability greater than this value, or go over this range. So it's equal to alpha. Now the same decision rule, that means this part, reject over here and accept, do not reject over here. So now, when the null hypothesis is false, okay, we take mu equal mu1. So this is mu1, all right? So in other words, forget about this pink curve. This is not true. Now we're looking at under the alternative. If the alternative is true, that's mu equal mu1. Then we look at this. So what's the chance that you reject the null hypothesis? So now the probability of reject the null hypothesis, all right, is this one. Because once you fall in this region, then you will reject the null hypothesis. So in other words, you will be good. I mean, you will reject the null hypothesis with a high probability, while not rejecting is so small. So it means maybe this is a good tool for us to do it. So when the null hypothesis is false, let's say mu equal mu1, then the chance of rejecting the null hypothesis is quite high. All right? So that's how we interpret the two hypotheses, or the beta and 1 minus beta. All right. Okay, so basically, the test procedure is to set up a suitable test statistics. So the one that I just mentioned is something like this, with sigma known, all right, to test the hypothesis concerning about mu. And we choose the value such that we have two regions. One is acceptance region, one is the rejection region. So just now, you can see that when, okay, so this is Z. So we said, okay, I test mu equal mu naught against mu equal mu1, where mu1 is bigger than mu naught. That means mu1 is somewhere here. Then my hypothesis, I will set this part, this region, and this region. All right, these two regions. One is what we call acceptance region. The other one is rejection region. All right, this region, we call it acceptance region. While this region, this part, is rejection region. So in other words, I decide on these regions. Okay, so basically I just have to decide on this value, and then decide on this value. All right, decide on this value. Once I decide this value, then I partition the range of the test statistic into two parts. So one part is called acceptance region, the other part is called rejection region. All right, so how to choose this point, or how to choose this region? I choose such a way that the chance of rejecting the null hypothesis is alpha. The significance level is alpha. All right. So the rejection region sometimes referred as critical region. So usually we will specify the rejection region. So the complement of it is the acceptance region. So once you have a sample, then you can evaluate the test statistic value and then check whether it falls in the rejection region or the acceptance region. If it falls in the rejection region, then we reject the null hypothesis. All right. So the value that separates the two regions is called critical values. It's called critical values. All right. So let's look at this example. So for the two-side alternative, test mu equal 3 against mu not equal to 3. All right. So these are the two critical values. That means we divide it into two regions. One is the acceptance region. So this part is the acceptance region. And these two parts are the rejection regions for two-side alternatives. All right. So these rejection regions are shaded. All right. And for one-side alternative, you try to check whether mu equal 3 or mu equal to some value which is bigger than 3. So if mu is bigger than 3, you expect that your X bar or your test statistics should be bigger. So you expect this side, all right, a bigger on the right hand side. So this is the rejection region. And similarly, if your alternative is mu less than 3, what does it mean? It means that you expect your test statistics to be smaller. So anything that's smaller than what you observe, oh, okay, we expect this is the value to divide into two regions. So you reject your null hypothesis if your observed value is less than this critical value. All right? So in other words, your critical value or the way that you divide into acceptance and rejection region depends on your alternative. If your alternative is mu bigger than 3, in this case, so your rejection region should be on the high side, on bigger value. While if your alternative is mu less than 3, then your rejection region should be on the left-hand side. For expect your test statistics should be smaller. All right, let's look at this example. So suppose we have a certain cold vaccine known to be 25% effective after 2 years. All right, so now we have a new and more expensive vaccine and supposed to provide a longer period of protection against the virus. All right, so what does it mean? So in other words, after 2 years, we expect the P equal to 0.25. This is the existing vaccine or the existing treatment. So we have a new one. So a new vaccine, and we want it to be bigger than 0.025. So we choose between these two statements. P equal to 0.25 is the existing for the existing status quo. All right, existing vaccine have this percentage effective. So I have this new one, new drug or new vaccine. I want it to be to show that it is better. Better in what sense? It has a more effective, higher percentage of effective after a period of 2 years. So this is my null hypothesis, and this is my alternatives. All right. So we choose 20 people and integrate with the new vaccine, and more than 8. Okay, I have not looked at the data, but I decide that if more than 8 of those received new vaccines past the 2 years period without contracting the virus, then we say that the new vaccine is superior. All right, so we already decide on the rejection and acceptance region without consider any statistics yet. All right, we just make that, okay, if the number of observations out of these 20 people, all right, shown to have past 2 years period without contracting any of the virus, then we say that the new vaccine is superior than the existing one. All right. So if this is my alternate hypothesis, so now I say that if X is bigger than X, that is my rejection regions. X is the number of subjects out of 20 people that is free from the virus after 2 years. All right. While the acceptance region is X less or equal to 8. All right. Because here it's stated more than 8, so that's not including 8. So this is the rejection region and acceptance region. All right. Later on we'll talk about how to derive it, but here we specify that. So how good is this rejection and acceptance region? So we have to calculate. Okay, so now we want to test the hypothesis P equal to 0.25 against P bigger than 0.25. And this is our acceptance regions, right? And this is our rejection regions. So we asked, what's the chance that we commit a type 1 error? All right? So X is the number of individuals out of 20, out of 20, who remain free of the virus for at least 2 years. All right. So we want to compute the type 1 error probability. So reject wrongly. All right. That means when X is bigger than X, given that P is 1/4, that means the new vaccine has only 0.25 the percentage of still effective after 2 years. But if this is true, and what is the chance, how likely we see X bigger than X? So we compute this. Remember, to answer this question, we need to know the distribution of X. X is a binomial distribution for 20 trials, and the probability of success under the null hypothesis is 1/4. So we just calculate probability of X greater than 8. So we add up probability X equal to 9, 10, 11, and so on. So the chance is 0.04. So this is the alpha, the probability of committing a type 1 error, or called level of significance. All right? So that means the decision rule that we have proposed have a chance of committing a type 1 error equal to 4%. But that's not good. We also have to consider the chance of committing a type 2 error. All right? But unfortunately, we cannot answer the question probability of X less or equal to X given X naught is false. Because we cannot compute this probability, because X naught is false means P is greater than 0.25, bigger than 1/4. So there are many possible values for P. So we cannot compute it. So what we can do is to specify, we can only specify a certain P value to compute the probability. So in other words, this probability of committing a type 2 error, all right, in general, we have to specify what is the parameter value, which is not the same as the null hypothesis. So I specify any value so long as it is not equal to 1/4 and also it's bigger than 1/4. That means it does not equal to this value, and also it has to be in an alternative. But I cannot take all, I just take one particular. So in this case, I take half. If you want, you can take 0.3. It's okay, because 0.3 is bigger than 0.25. So it's okay. So you can compute the probability of committing a type 2 error when P equal to 0.3, which is one of the values for the alternative. So here I showed it as P equal to half. All right, so I compute the probability, and the probability turned out to be 0.25. All right, so the chance of accepting X naught when X1 is true, and this one we specify P equal to 0.5. All right, so it is 0.25. So that means the chance of committing a type 2 error is about 25% if P is 0.5. All right, so the power of the test will be, of this procedure, is 1 minus beta. So it's 0.77483. All right, this is the power of the test above. So it is quite big. Okay, so in other words, if really this is so good, new vaccine, the percentage of effectiveness is still 50% at least 2 years. I mean, at the end of 2 years, then the chance that we can find out such thing is quite high. It is 75% chance that you will make the right decision by rejecting P equal to 1/4. All right. So let me just repeat this before we move on. So First of all, we have to set up a hypothesis. All right. Null hypothesis, alternate hypothesis. So the null hypothesis usually is the one that is the status code, and then the alternative is the statement that we want to establish. All right. If you have no knowledge about which direction to go, use a two-side alternative. All right. Then the next thing is that you have to set your level of significance, which is alpha, usually it's 5% or okay. We talk about type 1, type 2 errors. Type 1, type 2 errors. All right. So you have to understand these two ideas. All right. And then the probability of committing a type 1 error, we call it level of significance. Probability of committing a type 2 error, all right, we denote by beta. 1 minus the probability of committing a type 2 error is called power of your test procedures. All right. So we try to minimize the two types, but we cannot. Okay. So let's be more concrete now. We try to look at the actual procedures. Just now, the example, I define the rejection and acceptance regions without specifying how I get the idea. But now we are looking at a specific problem, testing concerned about the mean, how we set up my test procedures. So for the first discussion, we assume that the variance is known. That means sigma is known. All right? And the underlying distribution is normal, or the sample size is sufficiently large. All right? Because our test statistics is related to X bar. All right, so first look at the two-side alternative. So we want to test mu equal mu naught against mu does not equal to mu naught. So we know that if the underlying distribution x1 up to xn is normally distributed with mean mu and sigma square, that x bar will follow this distribution. Even if we just have x1 up to xn, and we only have the expectation of x equal to mu and variance of x equal to sigma square, but if n is big, then we still have these results approximately. All right? So under the null hypothesis, mu equal mu naught, then x bar is normally distributed with mean mu naught. All right? So that is the distribution of x bar under the null hypothesis. So first, let's discuss the critical value approach. Remember, the critical value approach is this is the critical value, so divide the region into two parts. One is the rejection region, the other is the acceptance regions. So for two-side alternative, unfortunately, there are two critical values. So that this part is the acceptance region, and then this part and this part, all right? These two are the rejection region. Rejection region. So we have two critical values. So this x1 bar and x2 bar. So we want to find these two values such that the chance that x bar falls within x1 bar and x2 bar. These are two constants. These are constants. You have to remember that. And this x bar is the random variable. So we want to look at these two constants such that the random variable x bar falls within this interval between x1 bar, little x1 bar and little x2 bar, all right, which is considered as the acceptance regions. All right. So once it falls in the acceptance regions, if the x bar falls in the acceptance region, we do not reject the null hypothesis. But if it falls outside the acceptance region, we'll reject the null hypothesis. So the rejection region will be x bar less than little x1 bar, or x bar, the random variable x bar, greater than little x2 bar. That means less than x, this is x1 bar, and this is x2 bar. So falls below x1 bar or bigger than x2 bar, we'll consider as in the rejection region. Okay, so this is the idea. So this is x1 bar. Okay, the value, this should be lowercase, x1 bar, x2 bar. So x bar follow a normal distribution with mean mu naught and variance sigma over root n. sigma square over n as the variance, right? So whenever x bar falls here, we do not reject the null hypothesis. But when x bar falls here, then we will reject the null hypothesis for a two-side alternative. All right? Okay, so how to get these values? That is most important. All right, so we know that this follows a standard normal. All right, I have to emphasize that all these calculations are under the null hypothesis. So when you calculate the probability to decide on your critical values or the test statistics, it's based on mu equal mu naught. As you can see, mu equal mu naught. We substitute mu equal mu naught. All right. So we know that this is a z between these two values is with probability 1 minus alpha. All right. A standard normal z between these two values minus z alpha over 2 and z alpha over 2. So this is standard normal and falls between minus z alpha over 2 and z alpha over 2. So if alpha equal to 0.05, 5%, then this value is 1.96 and minus 1.96 if alpha equal to 5%. All right. So what I'm going to do is to rearrange this so that x bar in the center. So this is a constant, this is another constant. This is my x1 bar. This is my x2 bar. So that the probability of a random variable x bar which follow a distribution with mean mu naught and variance sigma square over n falls between these two numbers with probability 1 minus alpha. So now I have my critical values so that I can make the decisions once I get the data. So I collect the data, look at the sample, calculate x bar. If x bar falls within these two numbers, I do not reject the null hypothesis. But if it falls outside it, I will reject it. And by doing so, the chance of committing a type 1 error is only alpha percent. That means the chance that it get out of these two critical values is only about alpha times 100%. Okay, so what we do is to select a random sample of size n, calculate x bar, and then we will reject the null hypothesis if x bar falls within this, falls outside this range. All right. If it falls within, we do not reject the null hypothesis. All right. So most of the time, we instead of using x bar between these two numbers, we try to use this statistics. That means we work something on this as a function of x bar. So x bar minus mu naught divided by sigma over root n. And this test statistics fall between these two numbers, all right, means that it is in the acceptance regions. Fall outside these two numbers, then it's in the rejection regions. So in other words, there are two representations of this test. One is in terms of x bar. Then you work out the little x1 bar and little x2 bar. Alternatively, you define the test statistic as z, which is x bar minus mu naught over sigma over root n. Then you compute this one once you got the sample, and then look at whether it's between minus z alpha over 2 or z alpha over 2. All right? So usually we use z instead of x bar. Okay, so let's look at this example. The director of the factory wants to determine if the new machine A is producing cloths with a breaking strength of 35 kg with a standard deviation 1.5 kg. So we take a sample of 49 and test and find out the mean breaking strength is 34.5. So is there evidence that the machine is not meeting the specification for the mean breaking strength? Now, so we are asked to whether it's not meeting the specification. And what's the specification about the mean? The specification mu equal to 35. This is the specification. And our question is whether it's different from this one. It did not say whether it's bigger than 35 or less than 35. So our new belief is that it's different from 35, whether it's shift. All right? So we set alpha equal to 5%. So our hypothesis, the first step is set up the hypothesis. So mu equal to 35 and mu does not equal to 35. Because in the problem itself, it did not mention whether we want to find out whether mu changed to a value less than 35 or bigger than 35. So we take in the two-side alternative. By the way, please don't start writing my null hypothesis mu equal to 35 and against mu h1 mu does not equal to 35 without saying what mu is. Maybe your mu is different from my mu. All right, so please say what you mean by your mu so that I understand what you're testing. So mu in this case is the mean strength of mean breaking strength of the cloth manufactured by this new machine. It's not any machine, any cloth, but the cloth produced by this new machine, and mu is the mean breaking strength of all the cloths produced by this new machine. All right, so the first step is to set up the hypothesis. So set up H0 and H1. All right, step 2 is to specify your alpha. So set up your alpha. You must say your alpha. I have not started looking at the data. That means I don't know the sample mean and other information about the sample. I just set alpha equal to 0.05. Next, all right, because in this case sigma is known, so our test statistic is x bar minus mu naught over sigma over root n. All right. How to get this test statistic? The idea is as follows. I have a statement concerning about mu, whether mu equal mu naught. So naturally, the first step is to get a point estimate of mu, which is x bar. Next, we look at the difference between these two. If this difference is big, then we suspect something wrong. If mu equal mu naught, we expect x bar minus mu naught should be small. But unfortunately, the magnitude between of this difference depends on the standard error of x bar. So we divide by the standard error of x bar, which is sigma over root n. So that's how we arrive at this test statistics. And we know that this follows a standard normal distribution. Okay, so this is the step 3 is to pick up the test statistics. So what test statistics that you are using? All right, and in fact, you have to specify the decision, how to make the decision. All right. So this is the test statistic, and your decision is based on the test statistic. But you must specify, okay, this test statistic I'm going to use. If it falls, okay, what happened to this one? Then I make the decision. So I would decide that because it's a two-side alternative. So whenever this value, when I take the sample, I observe it, is less than 1.96 or bigger than 1.96, then I make a decision. I will reject the null hypothesis. So my critical region, that means rejection region, is when z less than minus 1.96 or bigger than 1.96. But if it's within or between 1.96 or between minus 1.96 and 1.96, I do not reject the null hypothesis. All right. So the step 3, define your test statistics and your decision rule. That means you define your rejection region for critical approach. So so Z is the realization. I substitute the x bar by the lead to x bar. That means now I got the sample. I look at each value in the sample and calculate x bar. Then check this Z. All right. So step 4 is to do the calculations. So with x bar equal to 34.5, n equal to 49, I calculate that Z equal to minus 2.33. So Then I make the decision. So this part is the computation. The step 5 is to make the decision. All right. So since this number is less than minus 1.96, so my decision is to reject the null hypothesis. So I believe that mu is not equal to 35. Mu is not equal to 35. And I have to specify that the decision that I make is subject to 5% chance of committing and type 1 error. So I specify that, okay, I do this, I take the risk. I may reject wrongly. Because now my decision is to reject the statement mu equal to 35. So I have a 5% chance of committing the error, reject it wrongly. All right? So that's the critical value approach. So the idea is like this. So this is Z, all right? Follow a standard normal. And this is my critical value because I specify alpha equal to, there's a mistake here. So it should be alpha over 2. Because we're looking at the two-side alternative. So it should be alpha over 2. All right. So somehow the 2 missing. Okay, so now whenever the Z that you calculate falls within this region, falls between these two, I do not reject the null hypothesis. But if it is outside, I reject the null hypothesis. And since minus 2.33 is less than minus 1.96, so I reject the null hypothesis. All right? So you can see that minus 2.33 is somewhere here. So I reject the null hypothesis. In fact, for a two-side test and a confidence interval, they are equivalent. All right, you can see that H0 is accepted if the confidence interval covers mu naught. So that's the equivalent. All right, so you can see that. Now, this is the confidence interval. Mu falls between these two with 1 minus alpha. This is my confidence interval. Rearrange it, I have X bar falls within these two numbers, also 1 minus alpha. So the lower statement is the chance that X bar falls within the acceptance region with probability 1 minus alpha. And this event, the X bar falls within the acceptance regions, is the same as the confidence interval cover mu with a confidence of 1 minus alpha. So in other words, your decision of do not reject null hypothesis is the same as look at your realization of your confidence interval. If it cover mu naught, then that means we do not reject the null hypothesis. Cover mu naught. Okay, so here I just try to compute the confidence interval based on the data. So with sample size 49, X bar 34.5 and sigma equal to 1.5, I calculate the confidence interval between the confidence interval is 34.08 and 34.92, and you can see that 35 is not covered by the confidence interval. So in other words, we believe that mu does not equal to 35. All right, because the confidence interval does not cover the hypothetical mean under the null hypothesis, which is 35. So we reject the null hypothesis. So in other words, rejecting the null hypothesis in a two-side alternative is the same as whether the confidence interval cover the hypothetical value in the null hypothesis. Okay, there's a different approach to this problem. It's the p-value approach. All right. So what is a p-value? P-value is the chance that you see your test statistics more extreme. It's a bit hard. You say that more extreme than your observed sample value, given H0 is true. That is the p-value. And this sometimes the p-value is referred as also level of significance, but a different type called observed level of significance. So you have to distinguish between the two. Level of significance is the one that we set in advance. But the observed, all right, the observed level of significance is after you get the data, compute the test statistic, and then you in fact compute the probability that your test statistic is more extreme than what you observed. All right, so we convert the sample to a test statistics, obtain the p-value, and then compare the p-value with alpha. What is this alpha? Remember, it's the level of significance. So we compare, let's say it's 5%. So if p-value is less than alpha, less than 5%, we reject the null hypothesis. If p-value is greater than alpha, we do not reject the null hypothesis. What does it mean? It means that if I got a sample value such that the chance of seeing something more extreme than what I see, that means what I have already is very extreme. So I believe the null hypothesis is false, because the way that I calculate the p-value is based on the null hypothesis value. All right. So remember, p-value is the probability under more extreme under the null hypothesis. All right. So let's look at this example again. So in this example, all right, we have this testing mu equal to 35 against mu that's not equal to 35. All right. So we observe the test statistic, which is minus 2.33. That is from the data. After you got the data, you compute x bar and then compute. So from the data, you got x bar, and then from x bar, you calculate z, which is x bar minus 35 over sigma over root n. All right? That is then this one turned out to be, for this data, is minus 2.33. So now you asked, what is the chance that you see something more extreme than minus 2.33? All right? So, more extreme, maybe this is the extreme case, but in fact it's not. This is also an extreme. All right? Depends on how you look at it. For the mu less than 35, then anything less than what you see is considered more extreme. All right? So in that case, we look at this part. But what happens if mu greater than 35? Is minus 2.33 considered as extreme when you want to test mu greater than 35? It is not. So more extreme is that we look for a bigger test statistic value when mu bigger than 35. All right? Let me repeat it. This is my null hypothesis. If this is my alternative, all right? So I choose between these two. So what do I expect? I expect x bar under the alternative mu bigger than 35 should be bigger, which lead to a bigger z value. So now I got minus 2.33. I ask myself, how likely I will get something bigger than minus 2.33? Very big chance. So in other words, what I see is not extreme if I consider the alternative mu bigger than 35. All right? But on the other hand, if I consider mu less than 35, if mu less than 35, I expect a smaller x bar, a smaller test statistic value. So now I got minus 2.33. Is it considered as extreme when we consider mu less than 35? Yes. What's the chance that I see something less than minus 2.33? The chance is very small. The chance is very small. So my minus 2.33 is considered very extreme when you look at how small, whether the mu is smaller than 35 or not. So for a two-side alternative, we look at both. Then what to do? This is considered extreme when you consider mu less than 35. This is considered, okay, I should drop the word extreme. So I will have to look at the chance bigger. If I consider mu bigger than 35, I look at the chance of bigger than what I observed. All right? So what I observed is minus 2.3. Is it bigger than, what's the chance bigger than what I observed? Very big chance, 99%. So if this is true, what I see is not extreme. But if this is true, what I see is extreme. So how do I know which one? Because I only know that mu does not equal to 35. It can be either one. So what we do is take the minimum of the two. All right? The minimum of two. The minimum of these two probability. But we multiply by 2 in order to fit to the framework of two-side alternative to compensate. So otherwise it's not fair. So we look at both sides, compare, take the minimum, but we multiply by 2. Multiply 2 to fit to the level of significance. So we compare this 2 times it, all right? So it's 0.198. All right, so that is the P value for two-side alternative. Now at this point, maybe you are a little bit confused why we multiply by 2. But it's fair to multiply by 2 for two-side alternative when you look at the minimum of the 2. Otherwise, when you come to one-side alternative, you don't do anything, you just look at how extreme it is. So in that case, it's not a fair comparison because for the two-side alternative, you consider both sides, so you are more advantage. So that's why we have to multiply by 2 to enlarge the probability of rejection. All right. So, so this is how we decide. So if I go back to the problem here, so now I multiply this probability by 2, so the p-value is 0.198, and this number is less than 5%. Less than 5%. So I reject the null hypothesis, which means that based on the sample data and the test statistic value is minus 2.33, is considered as extreme. All right? And I reject the null hypothesis. Okay? Now, in order to appreciate what I just said, let's look at one-side test. So I test mu equal to mu naught against mu bigger than mu naught. So this is still my test statistics, but my decision is that whenever the observed test statistic is bigger than Z alpha, that means I will reject the null hypothesis if the observed Z is bigger than Z alpha. So this is the idea. So this is my Z alpha. If I calculate this value from the data and then it falls within this region, I reject the null hypothesis. All right. So even if I got a sample that the Z value is somewhere here, so yeah, this is extreme. But relative to the alternative hypothesis that we are testing, mu bigger than mu naught, this is not considered as an extreme value. Only this part is considered as extreme. All right, or this is the part of the rejection region. All right, so similarly, if the alternative is mu less than mu naught, then we are considering this part. This is the rejection region. All right, because we are concerned mu less than mu naught. Mu less than mu naught is alternative. That means if the true mu is some value less than mu naught, that means if the true mean is somewhere on the left side of the mu naught, then we expect x bar should be small. So x bar minus mu naught should be a negative number. So that's why the smaller the negative number, we consider is favor to the alternative. All right? So let's look at an example. So suppose, all right, the manufacturer of sports equipment developed a new synthetic fishing line, and he claims that the breaking strength is better than the market average, which is 8 kilograms. So in other words, we are looking at mu, which is the mean breaking strength. All right, this is our mu. So we are looking at mu. All right. So the manufacturer claim is mu bigger than 8. This is what he claims. So it's put as an alternative. better than, so it's bigger than x. So the null hypothesis is mu equal to x. Now think of it, this manufacturer claimed his fishing line has a stronger breaking strength. If you agree with him, we don't have to do anything. Okay? So everyone, I claim I'm a genius, I have IQ equal to 200, and you believe that, what's the bother? We don't have to test me. So I said so, and you believe, no need to do anything. All right? But now the manufacturer claimed his strength, the fishing line strength is bigger than 8. I have some doubt over it because the status quo is 8. So I want to find out whether his claim is valid or not. So that's why I put mu bigger than 8 as the alternative. And try to look for evidence to see whether his claim is correct. So that means look for evidence to reject my null hypothesis mu equal to 8. So suppose the standard deviation is 0.5. All right? So I select 50 lines, so n equal to 50, and the x bar equal to 8.2. All right? So we find out whether this has enough evidence to support his claim. So we use the level of significance 0.01. What does that mean? It means that we want to look for a stronger evidence to reject my statement mu equal to 8 and favor the manufacturer's claim mu is bigger than 8. All right? So I set 1%. So in other words, I need a stronger evidence. In other words, I need the average strength, the average line strength or breaking strength is much further away from the null hypothesis value 8 in order to reject the null hypothesis. All right, so step 1, I set the hypothesis, mu equal to 8, and against mu bigger than 8. Set alpha equal 0.01. All right, now if it's not mentioned in the question or tutorial questions or exam questions about the alpha, you set your own. You can either use 5% or 1%. All right. Then because sigma is known, so I use this test statistics, x bar minus mu naught, in this case under the null hypothesis 8, and sigma is 0.5, and sample size is 50. So this is my test statistics. Without looking at the data, I decide on the critical region or the rejection region. So whenever your Z is bigger than 2.326, I reject the null hypothesis. That means it's big enough. The difference between x bar and 8 is big enough to reject the null hypothesis. All right? So you notice that I write down a test statistic as a random variable. I specify my critical value, so the region is this one, which is in terms of lowercase z, which means that this is a constant. The critical region is bound by a constant. Less than this constant, greater than this constant is considered a rejection region. And this constant is to be the realization of the value of random variable z. That means I take a sample, I look at each one and calculate x bar, and then I can have this value lead to z. Check whether it's bigger than 2.326. All right, so I do the computations, and z turned out to be 2.828. So it is greater than the, okay, in fact the p-value, all right, the p-value. Because it's one side alternative, so the p-value is probability of z greater than what we observed. All right, because the alternative is mu greater than 8, so it is on the larger side. So we look at what's the chance that bigger than what I observed. All right. The reasoning is like this. I look at mu bigger than 8. So if alternative is true, I expect a bigger x bar, therefore a bigger test statistic value. So now I have this observed value, 2 point something. So is this considered big? Okay, look at what's the chance that you're bigger than me? If the chance is very small, that means I'm big. All right. So that's the idea. So we look at this probability, and this probability turned out to be approximately about 0.002. So it's quite a small value. So what does that mean? It means that what you observed is really a very big number. So what does it mean? It means that I should reject the null hypothesis because I believe X bar, because I saw X bar is big, and this is most likely come from the fact that mu is not 8, but mu is different from 8, bigger than 8. So that's why I have an X bar big. So that's why the difference here is considered as big. All right? So the critical value is 2.8, sorry, the observed value is 2.828, which is bigger than the critical value. So therefore, we reject at 1% significance level. And look at the p-value. The p-value here is also less than 1%. So the decision based on p-value is to reject the null hypothesis because the p-value is less than the level of significance. All right? So, this is the idea. Now I calculate. This is the critical value. All right, and this is my observed. This is the observed Z value from the data, and it falls in the rejection regions. All right, so I reject it. All right. Then the p-value approach is the same thing. So now I don't have a rejection region, but I look at the probability of the test statistic greater than this value. So this probability is 0.0022233. All right. So therefore I reject it because it's less than 1%. But now I impose the two approach. So you look at it, the p-value less than 1% simply means that what I observed, this one, falls in the critical region. They're the same thing. Why? Because this is the point saying that anything bigger than it, all right, bigger than it will have a probability, or on the left, on the right of it, smaller than what I have. So anything, so this is 5%. So if you are on my right, all right, here, then your probability should be less than 5%. So that's why the p-value approach and the critical value approach, in fact, are the same. All right? But the p-value has one advantage. So what happens if I change alpha? At the beginning, instead of using 1%, I use 2.5%. Okay, I set my level of significance, maybe, okay, not 2, but 5%, let's say. Then what, if you use critical value approach, then what you do, you have to look for the critical value and define your rejection regions. Although we know that if I set alpha equal to 5%, then it is 1.645 in fact. Okay, 1.645. That means anything bigger than 1.65, your test statistic value set, greater than 1.65, you will reject the null hypothesis. All right. But you have to work out this one. I remember that value. You may not. All right. But how about the p-value? I don't have to recompute what is the critical value. I can answer the question. If you set your level of significance at 5%, do I reject the null hypothesis or not? Of course, I will reject it because my p-value is 0.00233, which is less than 5%. Right? Whatever alpha, if I set alpha equal to 0.0123, this is my level of significance. Will you reject your null hypothesis? If you look for the critical value, I have to look for this Z alpha. All right? So you have to do some work. But I compare my p-value. I look at this, compare with this. This is still less than this. So I reject the null hypothesis because my p-value is less than your alpha. So I have a more extreme than what you thought. So I reject the null hypothesis. All right? So that's the, okay, yeah, I think I don't have time to, but the rest is just follow the same idea but use a different test statistic, which in fact we come across it in the last chapter. All right, so it should be not too difficult. All right, so I think I stop here. All right, and as for the the midterm test results, I will try to upload it to the Luminous as soon as possible, within this week, within these 2 days. All right. Okay, so Luminous, not IVLE.